Hello, what's up? I'm Junshan, and we're back on stream today. Um, I was looking at some of the streams that I once in a while I check my video producer thingy. Hey, what's up? What happened here? Some good stuff. Some subscription, but I don't have my chat and my things in front of me, so I don't know. Foregathers, thanks so much for the follow. Really appreciate it. Yeah, so I was looking through the video producer tab of Twitch TV web app, and realizing that there's a number of stuff I haven't exported to YouTube in my Comonadic Exploration series. So there's a whole bunch of stuff that's not that's lost in the ether, eaten by the ogre of time, Kronos, or the Titan. Yeah, but I did start to actually record locally my files because there were some encoding. Like the encoding is not always the best, and just relying on the remote server to do your recordings is super convenient, but from a quality standpoint, not necessarily always the best. So I started doing that about a month ago, but apparently I only activated the automatic recording together with the streaming sometime around the end of July. So I do have the first episode, I think, of my Comonadic series, and then the fourth, the fifth, the sixth, the seventh, and that's about it. So that's a bit sad, but oh well. It has happened to us before. Okay, so what are we doing today? We're starting with our good old housekeeping stuff. We start a log for the day, and yeah, I haven't actually looked at my workbench in a real long time, or even said what we're doing up here. And I realize I'm not actually sharing my screen, so I'll start doing that. That's going to be more useful. Yeah, so what do we do here? Well, I stream in order to work on some stuff and learn in the open, and hopefully that's useful to others. And a caveat is I do follow tangents quite a lot because that's how I learn. I drill down selectively. I'm more of a breadth first kind of person, so I don't go necessarily as deep as I can, although sometimes I do get lost in the weed and go deep. But that means that I'm kind of juggling with a lot of things at the same time, and streaming is actually quite useful for me to keep actually juggling with the same balls if possible. And what the ball we've been juggling for now for the eighth session is Comonads. I wanted to deepen my understanding of Comonads because we've actually been starting to build a prototype on top of a text-based CRDT to have collaborative text editing. And once we've done some work on the library, I wanted to build a prototype, and now we've been basically not doing a prototype, basically trying to look at which UI framework could be best to use the library, the collaborative text editing CRDT, which is called Chronofold. And I suppose I'm always interested in actually going a little bit deeper into UI frameworks, because in fact that's what led me to functional programming in the very first place. I was doing JavaScript on the front end and really tearing my hair apart away. How do you say that? Forget. Because I thought that it was really strange that there wasn't anything more principled out there. And that led me to FRP, that led me to certain flavors of functional programming, and Haskell eventually. And then I kind of bounced off Haskell and then was a little bit frustrated of my bounce, and then went back and been kind of stuck in there, hanging in there for a while now. That was maybe 5 or 6 years ago. So just to say, UI frameworks are kind of a good old, are motivating factor. So finding the right one is kind of something I've been the right one. The currently most usable for my view of software engineering at this point, and there's a few FRP-based frameworks that I like a lot in the Haskell side of things, like Dunai and Rhine with type level clocks. I like FRP quite a bit. I think I like arrow programming quite a bit, although I haven't done tremendous amounts of it. But there's something in the PureScript ecosystem that I find really interesting because it's very principled, is the Comonadic UI's work from Phil Freeman from a few years ago. And so we've been toying with that in our PureScript prototype stream series, and then I realized that I needed to kind of dive down into Comonads a little bit more deeply, because there were a lot of questions emerging that progressively in this series we've been actually elucidating somewhat, or at least becoming a little bit more familiar with the territory, which is Comonads. And part of that from quite recently, actually, I think I already dove down into UIs and whatnot. So I think I'm pretty much kind of here somehow. This Chronofold prototype, with the idea of doing some kind of PureScript implementation of the Chronofold data structure, and then maybe use that to do things maybe as streamer overlays. That would be something that fits more the kind of streaming tools use case that I'm exploring here. And yeah, we're trying to with implementing the causal tree merge algorithm from Chronofold, got some basic baseline performance measurements, and we're starting to work on the prototype. We had a bunch of stuff left to do, but then I kind of switched to exploring PureScript React Explore, which is exactly the Comonadic UI library that Phil Freeman created when he came up with this formulation, and trying to see how I can plug this maybe with other things that I've been exploring in the realm of more maybe streaming based abstractions. So we are kind of digging deep into this. This is where the Comonadic Explorations fit. But continuing to zoom out, I've been spinning a number of plates. And there is a big picture. There's something about trying to build tools for information integration, or maybe using Twitch and video streaming to maybe stream and develop and collaborate on more structured and semi-structured knowledge in real time. So that leads to a kind of a fairly ambitious goal, which would be to say, let's do something like an operating system. Maybe if it's not a proper operating system, maybe it's a kind of a layer on top of existing operating systems, which sort of speaks this language of knowledge integration or information integration. And some of that is maybe, you know, instead of switching between apps, maybe we switch between views of data, and maybe the data spaces are exist in sort of a more conceptual frame, and we try to minimize context switching by avoiding each application to have their own UX pattern, their own developed by completely different developers. We instead give back power to the users in how they structured access to their information by providing building blocks. So that's super ambitious. There's a number of things around how to do layout, how to represent knowledge. And so that number one, the big picture, is arguably the larger project, and there's lots of sub ideas that come from that, gathered from all the things I'd like to see in my that computers should be doing in my view but don't do yet. Drilling into that, there's knowledge management aspects, and for that we've been looking at a few different types of model. Like, I've been keeping logs for a while, right? But what would be better than that? Maybe something like Zettelkasten, which is used in research to organize knowledge with this kind of incrementally updated tree structure of topics, which are very well designed to fit the human mind. There's also the fact that there's spaced repetition and things like I'm going to note this because I watched Edward Kmet's talk again a few days ago on Stop Trading Water that he did at YoJam, I think, and is just great advice on kind of approaches to being, I say, genius consultant. And some of that is about maintaining a set of problems and a set of solution and do iterative deepening. And all of these are, I think, advice that can be, in some sense, materialized as rules inside tools. Then there's more onto how do we actually manage what's the fundamental units to manage actually knowledge, or maybe knowledge graphs more specifically, or conceptual graphs. And then we have another thread, which is, okay, how do we make the metal scream? How do we use all the how do we use functional programming languages to still use for instance, a GPU, and make data-intensive programs run fast? That's an area that I don't know very well, and one of the ways that we delve into that was to try and implement the n-body simulation using the Accelerate framework, which is a GPU-based programming framework for Haskell. And there's a thought also behind that, which ties a little bit into comonads, which it feels like this kind of problem should maybe be representable by comonads. And in fact, that's kind of how I bumped into this particular Stack Overflow post that I'm going to talk about in a second, because actually there's been some scientific announce that the three-body problem was somehow maybe not, if not solved, at least must have read his book, at least had a novel approach to being formulated here. Effective solution. So it's not that we found a symbolic solution for it, but it's that using, like, we found maybe a way to frame it in terms of more probabilistic walk, and that's quite interesting. And then it made me think, random walks, is that a comonad? And I think I searched random walk comonad, and then I found this post, which made some interesting assertions about comonads. But anyway, so, far from n-body problem, which is all simulation based and using this Barnett approximation, which doesn't calculate this at infinite precision, but using some way to cluster bodies and add and imagine that they are grouped inside their pull onto a one gravitational body that's far enough away is a bit like the sum of all the bodies with a kind of an approximate center that's sufficient for making things fast. So O(n) log n, I think. But maybe this approach might lead to a different system. It's basically acknowledging that it's kind of like a Drunkard's walk theory of random walks, and that there's different phases. There's phases where a star is ejected from a kind of center, and then when it comes back, then it kind of, there's a perturbation and a chaotic system for a while, and then it exits again. And that viewing the problem as such actually potentially helps to have a more probabilistic view of it. I looked at the paper shortly, but I didn't quite understand. But I thought it was interesting to even think about what random walk is like, because I've been doing Comonadic Exploration for 8 series, so I'm now seeing comonads everywhere, right? And I thought, the n-body problem is kind of, you know, like you focus on one body and you calculate the effect of all the bodies in your, let's say, store. It looks a bit like a comonad store, and then you move on, you focus onto the next body, and then you do exactly the same thing. So that feels like very much like a comonad in some sense, at least. And the funny thing that I wasn't expecting actually is that this random walk question is in fact a bit quite similar to a problem we've been asking for a while now in the Comonadic in our Comonadic exploration, which is how do we combine comonads with monadic effects. And that turns out to be what this post is about, because you kind of need to do that if you want to use a random monad, because the monad random specifically, for instance, is a monad. So here what leads to that is saying, well, you start with a Cook-Lisle arrow, why not? And then there's a R-Cook-Lisle, which actually goes to a rand B instead of a B. So basically saying, and that feels a bit like a profunctor, to be honest, that you have some kind of comonadic context and then you return into a monadic value. So, and then it says here that I'm going already deep into it. I think I should go back to this in a second. I'm just going to finish listing what I've been up to and then dive deep. So yeah, using the GPU is also a way to, yeah, basically making sure that I keep up to date with how to make software that runs on very modern architectures. And there's a little bit of folklore on that in functional programming, specifically in Haskell. Edward Metz contributed quite a bit on that, like modern way to be cache oblivious, to do succinct data structure, to do SIMD evaluation, and GPU is something that's been also looked at for a while, and I was trying to get more familiar with that. Also quite interesting looking at, for instance, the M1 architecture and seeing this kind of shared memory model between the CPU and the GPU, and Metal and Vulkan and all of that stuff is a little bit part of how to make the Metal scream a bit, and part of understanding what's happening also more recently in the compositing frameworks, for instance, that are most modern. Okay, and then I'm trying to also look at streaming tools, also using Haskell, with a way to think about video editing and video streaming in ways that maybe merge somehow. But that has become more of an excuse to think about free arrows, maybe co-free arrows, and more recently to think about graph state as the declarative bridge for a imperative library, which in our case is the GStreamer library. We've been basically trying to interface with the GNOME ecosystem and GStreamer in particular, including also what was called GNonLin, but I think it's now called NEL, non-editor editing. I forget the name exactly. And then we have a bunch of other stuff that we're looking at. But let's zoom back in. Our comonad work is described a little bit here, and we'll put pairing on the side a little bit for now, but the idea with pairing was is something that actually is starting to also take a slightly different shape now, so maybe I'll take a note of it actually. The idea for pairing is that there is such a thing as a way to say that two functors in some sense pair which means that when you have a functor of one kind, the other is able to perfectly eliminate the other one in the, I suppose, the elimination rule, like sort of sequent calculus sense of it. This is not at all my domain of expertise, but so this pairing actually is something that Freeman uses to explain a little bit the machinery behind the Comonadic UIs, saying basically it's possible to, first of all, say that there's always a pairing or a paired monad to an existing comonad, and that you can actually derive it automatically using the co-constructor, CO. And so the co of a comonad that you have is a monad that you can derive, and that is actually the pair of your comonad. And it just happens that doing the pairing like that means that you're in fact pairing a comonad as a space of a state space that your UI can take, all of the possible things that can happen to it, together with the actual action that your user take, and then your UI is able to interpret that into a new UI that is waiting for the next state. So you're kind of navigating inside your space, feeding each time a move, yeah, I find this very satisfying from a sort of understanding standpoint. I think it's a very clear abstraction, in my view, to visualize all possible UIs through this kind of spatial metaphor. And then it seems that Comonad has then really interesting properties in terms of their composition. In particular, composing side widgets, UI components side to side, nesting them, and things like that. And so Freeman gives us a number of existing combinators like sum and list and day convolution, which allows to basically lay out two UI components side by side and consider that the space that they can occupy is in some way the Cartesian product of each component space. I've come to sort of see things like this. I'm not sure whether that's completely true or not, but then I think then maybe sum is kind of one or the other, and I think there might be more of a ZP way to think about composition, which I suppose might not. I'm not sure what it means in the Comonadic setup, Comonadic UI setup. So I'm going to write that as a question, you know. So if the convolution of comonads is sort of like, that's a technical term, a Cartesian product of each component let's call them state spaces, then what is a ZP composition? ZP being pairwise. It could be that ZP actually could be that ZP convolution or composition works best in the time dimension rather than in the state space dimension. I mean, you can consider time as one state space, but that in fact it, like the ZPness would allow things to sort of independently move forward in time, and to say the way that a group of things move forward in time is just the way that the product of how each move forward in time, and that which implies maybe independence. So maybe ZP composition were best in time dimension for independent comonads. So maybe data dependency then in some ways manifests in some I don't know what, but some shape. Maybe that dependency shows up as something interesting. I mean, I would think that maybe it starts, maybe there's a spectrum that maybe the Cartesian product might play, maybe. Spectrum with Cartesian product at an end. I don't know. Okay, this is very theoretical and a bit blurry. What was I talking about this? I was in pairings and I was justifying pairs. And at some point in a few streams ago, we went kind of down into an existing library that Phil created, equivalent to what's in the adjunctions library in Haskell, where some of that stuff was called ZAP, and called it PureScript pairing. I started upgrading PureScript pairing to newer version of PureScript, and then also started adding some stuff that actually Phil himself had started adding in the form of what he called extensible co-effects. And so that leads me to some of the stuff that I wanted to talk about today, which is that I've looked at off stream, and I wanted to at least update myself and maybe write a few things in my log, and maybe, if we have time, play with some code. So what is it I looked at? Well, I finally looked at the CoEffect context-aware programming languages website, which is really the thesis of Thomas Petricek, which I realized after understanding a little bit better what's going on in the ecosystem, is a kind of a co-conspirator, of Dominic Archard, who wrote the Codo notation paper and a bunch of other stuff, and I think they all worked with Tamo Ustad, which is the kind of has been for now a while a bit of the powerhouse of research on comonads. And I finally looked at this, which I had not so far. And I gotta say, I was super enthusiastic about it because it really, in my view, justified my nine episode long now obsession with comonads in a way that I feel is very very stimulating. Basically, I mean, it. I'm going to write this down because I'm not sure. Like, this is PureScript. Hold on, PureScript. I'm not sure that that's so relevant anymore. Comonads. Okay, I'm going to write this in as a question. What if comonads were actually the building block we wanted rather than monads? We wanted is a bit of a, but that's kind of what I've been wondering after. I'm so far to be able to answer that question, but I suppose I'm on the way to try and do that because I've been trying to program with comonads, basically, right? Which is what Phil opens up by doing, by proposing to build UI components with comonads. But one of the key aspects of that, right, becomes, and that's sort of what we were exploring for a while now, is that same question of the random walk, and how do you introduce monadic effects inside a comonad, and does it even make sense, and is it still a comonad? And we've been playing with that for a while now, and I don't know whether we still found a solution, but I'm interested in looking a little bit deeper into coeffects to see indeed how they do that. I want to find out how to have an interpreter in IO or in effect, and full apply from here. Using the traversable instance of W and the applicative instance of F, which all of that sounds a lot like Kenneth Fauner's investigation into how to also, in his case, I think it's more about CFX, and was it? I need to look back at it because now I'm wondering whether it was part, I thought it was part of composing comonads. And I think it is, but I'm also interested in understanding how he ended up composing comonads, and that would be in his comonad sheet work, which we have somewhere here. And let's take a quick look at that. I don't think we'll find this easily here. Nested, yeah, I think he ended up abstracting over his composition of tapes using this nested type in order to keep track of dimensions, and that made things a little bit more complicated to understand. And so it could be that we need to actually watch or at least scroll through the slides to get back to, yeah, that's it actually, the functor swapper. Yeah, traversable and applicative. A traversable is a deal breaker apparently. Oh, but look at that, not aware of any functor that is traversable and is not a finitary container. And tapes are not a finitary container, but that's exactly, so that's hold on. That's not what's being discussed right here, but that's something that's been discussed elsewhere. And I have this somewhere on my phone, so let me take a look at it. And so not a random walk. There's the productive detour. Evaluating probabilistic cellular automata is Comonadic too. Productive detour. Comonadic. Oh, okay, I'm not writing. Productive detour, Comonadic. Here. And so this is actually part 5 that we're looking for. And there might be ascending representable functor. Go back in time. Okay, so visibly, oh, okay. There is just the part 2, okay. Yeah, he posted a question on Stack Overflow. So again, same problem, mixing. So it did come actually from that same Stack Overflow post, I think. My own probabilistic cellular automata and this blog post, yes. So it was Brad M, I suppose. And so it is still about, well, so I believe in the theoretical shape of the problem, I think, is this kind of like perfunctory Kleisli arrows. proclively arrow, whatever, right? Which have like some WA and some MB on the other side, and what that means. But apply to the specific issue of, kind of smuggling a monad inside your comonad, and what that means. And one weird thing that happens with that is that apparently, like specifically for tapes here, because U, I don't know what his U, yeah, no, U is here right now is a tape. So that's not written inside this particular post, but I think it's written in the first one. Yeah, U is a stream X stream X. And so that's an infinite stream, focus point, and an infinite stream. And that's a comonad. He wants to do a random walk inside this infinite line. And so he apparently reduces the problem to finding a traversable instance, which sounds exactly what Kenneth was trying to do. Meaning just to solve this particular way to pull a functor out, because that's the way to explain this with the types, I think is better done here, is that if you try to simply make your apply a WA to ren B by saying, oh yeah, but I just take B to be ren B, then you say, but let's just extend. But then the problem is that you actually end up with a W of ren B, when what you want is to end up with a ren B, a rend of WB. And that's exactly the same problem from Kenneth. And he goes and solves it with distributive. But weirdly enough, Brad goes on and solves this with traversable. And it's quite interesting because apparently, the reason why Kenneth didn't go that way is because they say that they're not aware of functors that are traversable, but that are not finite containers. And that's where things start to become a little bit weird, because in fact, it turns out that maybe it is about reasoning about laziness and strictness. And if you do that properly, then maybe you can reason about infinite traversals, but in a really strange way, because, for instance, for a tape, because if you I think use the Haskell semantics of the laziness of streams, then you would somehow need to kind of go through one whole stream before you actually start going to the other. So the fact that you have these two infinite containers, so if you have only one, it actually kind of just works. But if you have the two, it just works because you would be able to sort of say take 5 of that stream, and you would just calculate 5 times as much as you need, and that would be basically equivalent of saying, well, I decide that my container is finitary kind of after the fact, and we just, it's kind of like a loop. We let the container work until we choose to stop it, and so in that sense, then it becomes finitary at the moment where you stopped. So kind of weird, but it doesn't work with this U guy, and that's exactly why this Brad or Danny Diaz here uses this weird construction where he actually says, well, actually I take those 2 streams and I decide to kind of zip them, and so therefore if something is kind of consuming that, it's going to consume one element of each stream at a time. So using this zippiness means that you all of a sudden you make your multiple infinite containers at least what's called productive, which is a term used, I think, in theory to define something that actually continues to produce values at each iteration, which means that it has a chance to advance and therefore maybe converge for some for some cases, or at least not get stuck waiting for something. And so there's this really interesting interaction from 2013 between Edward Kmet and Conor McBride, who is big worker on Stack Overflow. And if you haven't seen it, by the way, check out Conor McBride's book that he derived from all of his Stack Overflow answers. And here there's a really interesting exchange there, because Big Worker says, first, there's some really interesting stuff there. First of all, they say that a traversal kind of defines the notion of left to right, which is something I hadn't really understood. Actually, I'm still a little bit shaky on understanding the difference between foldable and traversable. But in some sense, traversable seems to define that you have a way to go from left to right, or start at a point and then you'll always get a next point inside your data structure. And so Big Worker says, in general, infinite structures are not traversable, which is exactly what Kenneth says, right? Not aware of any functor that is traversable and is not a finitary container. Okay. So there's no good dist, and so that says stream maybe X and maybe stream X. And so we're right back into this distributive law, like moving the stream maybe outside the stream. And in that particular case, stream maybe X is of interest because it reminds me of data flow programming. Obviously, streams are kind of data flow programming, but basically a signal that would be defined as having it could mean several things. It could be a signal that, it can be many things. In fact, the semantics of what this data type is can be very varied. So in practice, you'd want to maybe wrap a stream maybe inside a new type and give it different semantics. So one of the things it could mean is that you have nothing for a while, and then at some point it starts giving you just until the end of time. And so that would be something like from a certain moment in time, the signal is present. And this is, by the way, connected, I'm pretty sure, to linear temporal logic and to also modal logic, which is in the essence of data flow programming by Tamo Ustalu and et al. And so if you define it like that, then can you make, so you, again, stream of maybe X would be defined with this kind of law that says it's nothing from the beginning of time, and at a certain point in time it starts being just, and then it's just until the end of time. And so the question is, can you define a maybe stream X instance for that? Well, I'd say yes, you could, and it would be nothing if the stream with that semantic in input is nothing all the way from the beginning of time until the end of time. And it could be just the stream of X, for instance, from the beginning of the moment where we receive just. And since a stream, unlike a tape, actually has a start, then you could make the stream start. You could say that this dist is the stream that starts, that kind of lets go of all the nothings. It's the one that starts from just. And then you could define other semantics too, right? But I think once you define, there's no good dist if you don't give your stream a particular meaning. I think there's no the other meanings you could give are meanings where the stream has a just value from the beginning, and then at some point is nothing, and those are streams that terminate. And if it stays nothing until the end of time, then you could say, well, it's just to make it a maybe stream, you could maybe make it nothing if it's nothing from the beginning until the end of time, same thing, and then maybe make it just the same stream in that case. Why not? Which is then not very symmetric with the first definition I gave, but whatever. But I think there's other semantics you could give to this. Hey, Chiroptical, thanks for the raid, really appreciated. How's it going? I saw you were streaming earlier, doing some keyboard things. Hope you're getting fast with that. I'm terrible with keyboard. That's why I'm just spending a lot of time talking right now. But right, so the semantic of the stream could also be nothing, and that I haven't seen that meaning in a lot of places. It could be something where you have nothing from the beginning of time, and then at some point you have just, and you have a few values, and then the stream sort of shuts down until infinity, for instance, right? So that's another semantic of a stream. It's a stream that can go on and off. And then I suppose the maybe stream X for that could be, well, if it's nothing all along, then it's nothing. But if it's the stream that has some values in between the nothings, then you could maybe make it a just of, let's say, again, the same stream. You dislike new RAID systems. What's changed in it? I haven't been following that. I have too little viewers to ever RAID. I think I did it once. The keyboard is crazy hard to use. Oh, right. Is it one of the? It's one of the separated hands thing, right? Yeah, I feel like I don't have the courage to get back into building a whole new muscle memory, neural network to do that. Yeah, exactly. Rebuilding muscle memory. That is the way. That is the way. Right. So, I was saying, like, I'm looking at this fairly abstract problem again of swapping of like what is sometimes called a distributive law, something that allows to pull a functor out of another functor. And that was used by Kenneth Foner in this talk to try and make recursion inside his Comonad work. And I just seen this same problem pop up in like lots of different places, including this place here. You press read, then substream. Apparently say something in chat. I see. Huh. Oh, yeah, it's like you have to say something in chat in order for things to read. Yeah, I see. Very intuitive. Right. Yeah. Sounds like they should have at least like something a little bit signposted. If you have to read the docs each time you raid, it's probably not very well designed. So this overall problem, Kenneth ended up solving his particular problem by not going into traversable because he says it's a deal breaker because you cannot, because there is no traversable instances for non-infinite containers. We are not aware of a not affinity container. Double negation here. Basically, there's no traversable for finite containers, apparently. No, sorry, infinite containers. So I get it wrong. And but apparently that's not exactly true, according to the folklore and this conversation between Conor McBride and Edward Met that I'm trying to progressively get into. And where was I? I'm a bit lost. Right, dist. So dist is one way to think about traversable. And I think basically Kenneth went into using a distributive instance, distribute, which has the same shape, instead of this particular sequence instance, doing some type Tetris here. Instead of using sequence, which requires traversable, he went and used distribute, which requires distributive. And so in his case, it works. But, but this other thread here, which is the reason why I'm looking at this in the first place, is how do you combine monads with comonads? Like how do you, and the reason why this is interesting is because of this notion of co-effects, which is basically down to if you have a Comonad and you want to program with Comonad, that's great. But then how are you going to, in the end, run something in IO or run something in effect in PureScript? And the way that Phil Freeman proposes to do that is some particular way, and we went down that rabbit hole quite deep in the past couple of streams. But now I'm looking at it from a slightly different perspective, because I bumped into this kind of similar this problem being formulated in a slightly different way, but it's actually the same problem. Here, the problem is, how do you run your Comonadic computation in rand-B, which is the monad random library? So you could very well see IOB here and say it's the same problem. It's how do you mix a comonad with a monad? And their solution, which really has nothing to do, as far as I can see, it probably does, but I can't see it yet. It has nothing to do with the way that that Phil Freeman does coeffects. And also, I definitely can't see how it connects to coeffects as they're defined by Thomas Petricek. And I come back to this because I've learned a lot from this particular thread. But just to finish on this one, this particular way to think about how you mix a comonad with a monad is to say, you just you extend your comonad as you would any comonad by using your WA to A, basically using this type signature and saying, well, for B I take rand B, and then the problem is that I get a W of rand B, whereas what I want is a rand of WB. So we see we have exactly that same shape of the problem of trying to basically sequence effects or distribute the monad around the comonad here. And since both are functors, it's the same as distributing as dist or distribute. And what's interesting is that if you look at it from the sequencing standpoint, which is sort of this standpoint, saying, okay, I'll use sequence A in order to apply my T effects. Well, then your T effects need to be traversable, and apparently there's no traversable for infinite containers. But it seems like both Kmet and this gentleman, Barry or Brad M, sort of show that actually you kind of can. So what Kenneth says here, that infinite streams are definitely not traversable, might not be true. And that's weird and very interesting, because the way that it's not true is by doing what I was saying earlier, which is that indeed, with the laziness of Haskell as is, if you take a tape as being an infinite stream, an X in the middle, which is the place where you have the head of your tape, and then an infinite stream on the right, then with Haskell you'd be a little bit stuck, because to manipulate any value of that, you'd sort of, being lazy in only one of the streams would mean that you'd sort of wait until you finished consuming your whole stream before you'd be able to consume the or even start on the second one. And so that's actually, interestingly enough, exactly the problem that Chris Penner ran into in another Stack Overflow post when trying to do recursion schemes with comonads. Well, so that's not the one. Comonadic fixed combinator, that's the one. So apparently inspired by the same Kenneth Foner video, Chris went on and tried to implement the fixed point operators for monad and comonad and comonad apply. And he bumped into these laziness issues, and one of the solutions provided here was to say use irrefutable patterns, because that would make it so that the GHC won't wait forever trying to figure out whether the thing is of the correct type, because it's actually waiting for basically stream to be available before being able to start on the next stream. And the way that Brad solved this particular problem is by coming up with a traversable instance, and he creates. He asked this Stack Overflow question saying, "Is that a valid definition?" And that's where Conor McBride and Ahmet chip in. And so his way of doing this, as I was saying earlier, is that he makes it so that instead of having to wait for a whole infinite stream to be consumed before you can get started on the second one, you kind of zip them, and then you start basically consuming them pairwise in this kind of zippy fashion. And one way to look at it is to say he's consuming them instead of left to right, since with this kind of left infinite tape, right infinite tape, you need to consume the whole of the left infinite tape before you start consuming the right. That doesn't work. You zip them, and then you start basically consuming them from the center outwardly, because that's kind of like consuming them in pair. And he says traverses outwardly, and that's very interesting. And I basically, by doing that, and there might be, I don't know if there's a general solution to that, but anything that's infinite that you can zip, then in some sense can become traversable. At least that's what I understand from this exchange between Conor McBride and Edward Met. So let's dig just a tiny bit into what they say here. What they say is, well, so Conor McBride said infinite structures are not traversable because there's no good dist. But here I was saying, actually, I think there are dists for certain things. And just there's one particular shape or semantics of stream maybe X that I haven't talked about. I've talked about stream maybe X as being just from the beginning and then nothing, which is the streams that terminate. I've talked about streams that start from a certain point, streams that are delayed stream, like have nothing for a while and then adjust and then just for the end of time. I've talked about a stream semantic that I haven't seen much. And by the way, those two first semantics, they are in the Essence of Data Flow Programming by Tumo Stalu, where he looks at using Comonad as the basic foundation for data flow programming. The third one that I haven't seen is nothing from the beginning, and then at some point just, and then at some point nothing again. So that would be a stream that would actually be isomorphic to a list. So it would be basically a valid way to actually have an isomorphism between a list. So a finite tree container, finite tree container, and infinite container, by saying my list has nothing, and then it starts, and then it has nothing again. I'm kind of being confused, I think, with I'm sort of describing tapes all the time by saying nothing from the beginning of time, because streams, I think, are only are infinite until the end of time. They have a head. They don't have the whole history, the infinite history. That's the tape. Right. So the final type that I haven't talked about, what I was saying is that I think you can find a good dist for all of these semantics, and but there's another semantic, which would be the stream that can be on and off at different times. So it can be nothing, and then it can be just for a while, and it can be nothing again. It can be just for a while, and I think those are partial streams, and I think maybe those are actually defined in in Essence of Data Flow Programming. Pretty sure they are. Should I open this Essence of Data Flow Programming? Partial streams. The partial streams are actually allow to do to compose streams of different with different clocks, which is pretty cool. Yeah, so that it does exist, and then there's a dist for that. Actually, look at that distributive combination right there. So is that new compared to that conversation? 2005. It is not. So yeah, partial streams I think can have a distributive instance. In that case, what is it? Dist prod? What is prod? Okay, maybe I won't be able to go back directly into this, but it seems like this is fairly well treated here, including the stream of maybe A's. Oh, actually, prod maybe might be stream, actually. So distributive instance for the stream of maybe, but stream scenes as a particular easy easy comonad. I don't know if it's the one that's isomorphic to stream, but yeah, just one of the important contribution to this, which I want to explore at some point and build a library for in PureScript, is the RVS monad, which is a good way to have a comonad that gives you the ability to talk about things in the future and also keep a certain history of things in the past, which is something that is talked about in the co-effect paper that I'll go back to today as well. Okay, so we've talked about 4 semantics of stream maybe X, in which I think we can define a dist, which applies to semantics, but doesn't apply to all streams. And but arguably, if you see maybe as failures, then the most natural semantic for this, because maybe is often used for that, to model programming with exceptions, right? Programming with non-tagged exception. Then you could say that stream maybe X is a stream that interrupts itself, and then maybe stream X is therefore it's nothing if the stream's been interrupted at any point, and it's just if the stream is never been interrupted. And you could say that I suppose this dist needs to be productive, right? It needs to it's only at the moment where you stop the program that you know what your value is, which I suppose is the tricky aspect of this. So the fact that traversable defines the notion of left to right is super interesting. Relies on laziness that not all applicative processes. So it's still clearly making Connor think a little bit. And but then this user says, would be inclined to say that there is no reason that an infinite structure cannot be traversable, which obviously goes against what we've seen. That seems to be the folklore, that infinite streams are not traversable. But it does require laziness that not all applicative functors, I suppose, support. But so would an infinite list, of course, which is traversable. Haha. That's true, right? So how come then an infinite list is traversable, but then infinite containers are not traversable? What's up with that? Also, there's a lot of options for the specific dist function for maybe a cross stream that you mentioned, although traversable instances usually don't satisfy it. For example, the first item is nothing, the result is nothing. Otherwise, the result is just yes. And that's back to the semantics. Here's the gist with the full code. That's Danny Diaz here. And he needs to use sequence to aggregate monadic effects inside a comonad. Someone forks the gist, including Sword-Vischer's correction, the first revision. I think that's Sword-Vischer is providing some answer here, which we'll also look at. Okay, then Dark Otter. So maybe user 8824425 was Dark Otter. Define filter for stream in a manner which ensures its productivity. So that is where things start to become more theoretically grounded. It seems like maybe if your infinite container can be traversed productively, then maybe you're fine. Meaning you're always getting new information at each iteration, then you're good. And then another user, so maybe anonymous, says, by that I assume you mean in a way in which it is guaranteed to terminate, or at least get each next item in a finite time. Yeah, that of course is not possible to guarantee. There is no way to know how far you might have to look to find the next just x value. The same is true of filtering a normal list. Give filter 4 equal $4 repeat 5. Yes, exactly. So but that's no, it doesn't mean that you get the next item in a finite time. It means that I think each time you're processing an item, you can get an answer. And if that's the case, then the moment where you get your 5 or your 4 in this case, then you have a 4, and then you add the thing, and then you continue having 5. Well, you keep on having 5. You don't have a you can just continue to do work at each iteration. And then Mr. Kmet comes in and says he's taken to a different way of thinking about traversals. We use infinite traversals all the time. So again, contradicting this. So I wonder, it might mean that there is a sequence A way. Okay, I'm going to write this down because I can. I think that should be explored at some point. And because also I have Comonad sheet in the list of things that I want to do. So it's given the thread. So given this, it might be possible to write Comonad sheet and I think cfix and maybe kfix, which was the thing that Chris was exploring here. That's pretty. Both. Using sequence A rather than distribute. Distribute. And I'll also link to the particular contrary to what Kenneth thought. Okay, so that's a dendrite to explore. If we're productive enough, we might at some finite amount of time get to that dendrite. And so that's quite interesting. And then just finish with the understanding what Short says. He seems to think that there's two other requirements by traversal for traversable that, and in particular, I think we break the second requirement that fold map should be equivalent to traversal with a constant applicative functor. Is that the thing? The two laws? Yeah, the traversable define what left to right mean. That's so cool. Functor instance f map should be equivalent to traversal with the identity applicative functor. Probably was this as blah. F map get compose traverse f compose. It's not the same. So seems to think that I know that creating their own instance for foldable. Okay. So it's just a law that is about how traversable relates to foldable, and if you define your own instance of foldable such that it's productive, then it's fine. So all is well, and potentially this is a lawful traversable instance, and the fact that it's possible to traverse. The fact it means that anything that can be traversed outwardly could be traversable, and I think that's pretty cool if it gives us something to evaluate effects. So I think So in this, now we zoom back. We zoom back to the idea that we want to interleave effects with our comonads, right? Which is what is sort of promised by extensible coeffects here, and seems to be, and is something we still haven't really succeeded in actually. No, I think we have succeeded in doing it, haven't we? Hold on, let me go check out some of our code. I think Comonad composition. I think recently we have been very close to running this. Yeah, we needed to have run Coty. We need to rewrite an explorer that took run Coty into consideration, but we were able, in our example, to create an ink for our Comonad for our counter component. We gave a counter interface that has these two actions, and we defined the corresponding monadic value, being able to use a base effect in effect. And we proved that we can do that with the types by logging an effect at the same time as we process our or create, how would you say that? Yeah, that our monadic value is able to, in addition to doing the right comonadic thing to eliminate a monadic value, it's also able to have an effect in the base effect. And there's this weird thing where it needs to be in both, which I think means that probably we can go deeper than Phil has, I think. I'm not sure yet. It's really weird. And then there's also the fact that we can do that also in the interpreter if we want. And that's a bit cleaner actually here. And we can log the effect. And then the interpreter can be passed around from the top. So here we do this here. We pass an interpreter to our counters component, which is in fact a list of counter here, but doesn't really matter. And we pass that counter interpreter to each individual instance of counter here, and then the interpreter then is here, and parameterized is the component, and then we pass it even down to the step function, and we then use the interpreter initialized with the state that we need to thread through. And threading through the state here could probably be done through a store comonad, I think. But let's write that down as well. Maybe I'll have a, so I think this stuff is to do in yeah, that's in what is it called? Comonad composition POC. Comonad composition POC. And one of the other thing I was saying right now is, right, well, there's a few things here. Step counter and interpreter take a count initial state, threaded state, that can probably be abstracted via store comonad. And then there's something maybe even more ambitious here that came up when I was looking things up, which is this idea of comonads and recursion schemes. And that actually might even be something that that make comonads sort of why that kind of justify what if comonads were actually the building block we wanted rather than monads. Yeah, right. What if? Because here are a few examples of comonads. One is data flow programming. It seems to be completely defined by comonads. Things like well, game of life. That it's not super interesting. I think recursion schemes is really actually one of the most interesting things. And then Comonadic UIs. Also because they're a smaller language than monads. Such that you can get a monad from any comonad, which is not the case backwards, not the case the other way. So if you use comonads, then you always get your monad for free. Whereas if you use monads, who knows, you might fall into some space that actually doesn't have comonads. I mean, it's still very abstract, but usually we like smaller languages. And in fact, if we can compose comonads with IO in a principled way, then we still have the full power of monads if we need it. And so yeah, recursion schemes. And this is a really cool blog that I hadn't seen until today. And that's one of the other things I wanted to report back on, is this idea that actually all recursion schemes can be, and distribution is again the name of the game here for some reason. You can define a generalized catamorphism and a generalized anamorphisms, which can be used to define all other recursion schemes. And this is, by the way, a translation of a paper that's earlier than the essence of data flow programming from Tomorrow's Taru. That's recursion scheme from Comonads, and of which we'll have a PDF here. And so you can get arbitrary recursion schemes from comonads, and you can use comonadic composition, and that's a little bit back to this question of like the different types of convolutions of comonads, because it seems like here we use this distributive way to do comonadic composition, maybe, and that gives us something that makes sense for recursion schemes. Yeah, if we parameterize, so base T, I'm not sure what it is. I think it might be something that looks maybe a bit like resume in pure script run streaming, like something that has a done and a continue, like a maybe like fix in some ways. Let's look at it, because so that's from Edward Kmet's package, and let's see what. Let's actually go to the GitHub and check out the base and see what that guy. Ooh, that's a bit. Where is the definition? Listf base functor of list. UK. Yeah, that makes sense, but where is base? Database. Type base. Okay. Tree. Oh, so those are existing base functors. Okay. So foldable. Maybe that has the base. Oh, yes, it does. It's a type family. I see. Right. But it's about recursivity. So I think it is, I think, in spirit, sort of like this guy in PureScript run streaming. Let me show it. Step. Is it? No, maybe it's not step. Resume. Next, and then a next thing, and then done. I mean, that looks like a melee machine or more machine or a machine in the machine library from Ed. I'm not sure. Yeah, I would need to investigate much more to understand base T here. But the fact that it gives rise to the ability to recurse, meaning unrolling one recursion layer at a time, I think means that it's fairly similar to I think this idea, and probably to the essence of data flow programming, and probably just it's this idea of abstracting over a loop, which is the essence of recursion. And so yeah, with composing this base T thing, which basically is the essence of a loop, would be better called maybe loop, with composing that with a comonad, allow you to create different recursion schemes depending on the choice of comonad. So if you choose identity, then you have a catamorphism. If you choose tuple, the tuple comonad, then you get a paramorphism. And if you choose the co-free comonad, then you have a histomorphism. And so this kind of parametric behavior, like swap a functor, swap a comonad in this case, and then get a new recursion scheme. Even more than that, combine now, use a comonad transformer and combine those things, which is exactly what the rest of the blog post here looks at. Is like now if you use, he uses an example of a ledger that tries to combine empty and histo, and then he sees that if you define that you can define your dist no, that's, where is it, that there's a way to use the comonad transformers, dist para t, in order to automatically combine the dist histo distributive and the disparity distributive to give you a distributive instance for the comonad transformer composition. So by the way, okay. Comonad composition. It just feels like there's a zoo of that. There's comonad transformers which rely on a distributive instance. Could it, and maybe that is also a question about traversable. How about traversable? And then there's things like day convolution, and that seems like a completely different thing. Convolution, no, convolution. But is it an instance of transformers with a specific distributive instance. I can imagine that. In fact, let's see whether we can go to the deconvolution. Okay, we need to go to functorial.org, com, and deconvolution, Comonads and deconvolution. Deconvolution of two functors and another functor. And they take something that looks a lot like Zap, by the way, which kind of makes me think that maybe pairing is actually a, holy moly, that's another thing, but is pairing Zap a form of deconvolution of comonads and monads, where deconvolution of comonads would give you what Phil is interested in, but that deconvolution of comonads and monads will give you pairing. I mean, this is really pairing. Wow, very cool. Turns out that there is a valid comonad instance for DFG whenever FFG are themselves comonad. Right. So, and the way that this works is by defining the, let's call it pairing function to be composition or wrapping of f and g. But you say that it's symmetric, but that's not symmetric, is it? Or maybe symmetric doesn't mean commutative. What does symmetric mean, really? Swapped, I think is where this was pointing. Yeah, swapped. The monoid for deconvolution. Monoid? Oh, on the Cartesian monoidal structure is symmetric. Fmap F swapped. All right, okay. So DFG equal DGF. But then how would that work if... Oh, I mean, this is the functor instance. It's not the day instance. Does this make sense? DF is a comonad transformer. Okay, so the comonad transformer is symmetric. Is that, does this make sense? DF, I'm not sure. I'm not sure if it's supposed to be symmetric in F and G. I mean, according to this, it looks like it should be. Who's Eitan Chatav? Mathematics. Oh, mathematics genealogy project. That's cool. Theory of categorified quantum S12. I see. Okay. GitHub. Elliptic curve cryptography. Audience. Error continuations to err is human. Meetup. And August. Morphism tech. 3 categories. What is that? It sounds interesting. Mathematical software consultancy. Well, that's Eitan's consultancy, looks like. No website. And deep embedding of SQL in Haskell, 3 categories, index transformers. Oh, that makes me think of a thing. The store arrow. Go Kleisli. There's something else that I came up while drinking my coffee this morning. Arrowizing the store comonad. And so that's something that I think I keep having some hallucinations about, which is that there's something like there's profunctors in some places, that this whole monad construction that maybe has profunctors, and I think that this makes this potentially precise. And in fact, this particular library, this one, the arrow transformer library fork, which contains a arrow version of the store comonad. So that kind of blew my mind, but then looking at it, I'm like, oh, but that completely makes sense, actually. That, you know, there's this whole idea that potentially programming with arrows is a more general setting than programming with monads. And that is, what is it? Programming, who said that? With arrows. Trying to remember, that is Hughes, a very respected John Hughes, who is the Quick Check developer, and was keynoting at the BobConf this year. So say that you can generalize monads through arrows, but would you believe that? You can apparently generalize comonads through arrows. And it kind of makes sense, and I wonder whether I didn't fall into this already when I was playing with arrows in one of my previous streams, which was this idea that there was the possibility, well, in fact, it's actually the Dunay formulation of arrows that is quite conspicuously looking like it could also be extended to something more general. Let's see, where are the actor design pattern? I don't think I've seen that one yet. No, I have not seen that one. Ooh, exciting. More things to look at. Okay, maybe I just go to the MSF definition in source, and I think it's in data, and it's actually in Comonadic stream function and internal core, I believe. And we have MSF, and what is an MSF? It's an arrow, and it's a monadic arrow. So already it means something. It's something a little bit different from, well, yeah, it's a Kleisli arrow, which returns something in the env, in like some kind of tuple, which hints at some state monad there at the bottom, and then carries on. And yeah, conspicuously, it's like, why won't you put like a WA in here or something? And then what will happen? And then you have an MSF WM AB. Or what if you start moving all of your stuff in here, all of your context? Like, can't you do that? And I think you can. You can. I mean, I don't know if that's completely reflected in those types. And I think, yeah, I'm not sure how that works, to be completely honest. I forget a bit what is the dealio with how arrows are defined. So I'll definitely go back to this at some point, but basically I think this is still going from an A to a store S of B, maybe. Okay, I need to write this down into some kind of question that makes sense. So that's not really related to comonadic composition. That's more of a question that I think I've been having for a while, which is what's the relationship between comonad monad pairing in time, which by the way is also about the Delco-free and the recursion scheme in there, and the kind of the mealy Moore machine thing, which we've seen also is in the machines library. Maybe that's another place to go check out actually. The machine, the mealy T documentation points to Dunai's monadic stream functions. So the question is, did Ed somehow also see that there were potential comonad transformer that could be attached on the context side of things? I'm not sure, but there is this whole what is it? Y? No, it's not Y. There's this thing about having several inputs, which is the is, I think. Yeah, the is. So the basic definition of a machine, is that going to be here? It might not be. I think is a process, I think, is one of the machines. Yeah, that's right. So is A, process AB is single value A to a single value B, whereas a machine is more generic than that. It can actually take any number of inputs. So is the taking of any number of inputs comonadic? Is comonadic? Might be. Is that comonadic? Because it kind of wraps the inbound arrow, and therefore then when we create machine T, the M wraps the return type, I think. And that's all good, but maybe we can also wrap the input, and maybe that's comonadic. And if not, maybe because the pairing is actually not in this dimension, maybe it's not about wrapping the contravariant, or it's really not a, if it's an arrow, it's not like a function, so I don't think you can I wonder whether it's okay. I need to also ask these questions. In arrow A to B, is A contravariant? Or is that just for the function instance and other such instances? Because for instance, I don't think like I think you can have a rel instance of arrows where A and B is not that things go from A to B, but it's that A is somehow related to B, like because it's the same, because it's related to in a kind of database. And in a relational language, then there's no real contravariance. Things are symmetric Let's think. That would be a way to say it. So, but maybe it's not about wrapping the input of the arrow. Maybe it's about the way that the maybe it's about writing reactimate as a comonad or something. Meaning the way that we consume a stream of these kind of monadic values with an interpreter on the back. And then that's kind of like a driver in the cycle.js view. Something like that. Okay. So that's quite a deep rabbit hole. I'm going to take a small break and drink some water and such. I'll be right back. Oh, my video has frozen for a while, apparently. And here it is. It's back. And it's back, but I'll be right back. All right, I am back for maybe 40 minutes more. It's when my food will arrive, so let's go for it. Yeah, so I'm thinking there is a way like that. This whole wrapping comonads in arrows. I want to keep this somewhere. Here, wrapping comonads in arrows. That is something pretty interesting, because ultimately I do want to program with arrows. So seeing that that would actually allow me to program with comonads as easily as we're using this library is super awesome. I don't know exactly what shape that will take. I think, but I think it will in some ways start to converge not just this Comonadic UI ecosystem, but I think it will converge FRP too. That's sort of basically I think what I'm talking about here. So let's be crazy and write it down. Comonadic UI merging yeah, that will do. Okay, and the water here. Okay. Yeah, that looked very interesting, and I was actually looking at this because Eitan Chatav is the one that introduced Ed to deconvolution. The convolution of two covariant functors is a covariant functor, usually defined in terms of contravariant functor. However, this needs a monoidal category, and has-op is also monoidal. Convolution can be used to nicely describe monoidal functors and monoidal object with request to this project. I don't understand that, but that's okay. Right, so, and we saw that Eitan is, well, very smart, clearly, and I think I might have seen free category before, because that's actually arguably the going even further than having free arrows, which we've looked at. Okay, I want to take a quick look. Quiver. Oh yeah, isn't a quiver? Oh, I forget what a quiver is, but that's a quiver. It's a free category on a quiver. Is it a thing with an edge and two? Yeah, that's the. Is that the type of edges and that the type of objects? And you have a source and a destination. Announcement. Announcing free categories. Category type class in a Haskell project doesn't get much use, which is a real shame. I mean, Haskell is familiar with it. And the path. And path P is the free category or path category with steps in P. Okay. Oh, he uses it in Squill. Ooh, I feel like I'm gonna like this. And if we have Kleisli, we'll have Kleisli, and I think, yeah. I mean, what I thought is that free arrows will give me maybe a language to create arrows out of a base functor. I don't know whether that's the right way to think about it, but quiver is a pre-category. The categories have object and morphism. Quiver have vertices and arrows. So maybe that is it. Maybe that's arrows and those are vertices. Directed graph, because the edges are arrows and have directions. So it's called multi-digraph. Maybe multiple arrows between vertices. Oh no, okay, it's just a multi-digraph. So that's an example of a quiver. That's just not the definition of a quiver. It's a thing where there can be several arrows between two edges, two vertices. Okay, excellent. We like that. Eightfold path. That's an interesting reference there. Category, queer morphism. API could apply square migrations. Ooh, he uses this for data migrations. Okay. So that's completely a tangent. But we follow tangents. therefore. But putting this in the Comonad log doesn't quite feel right. Well, wow, it uses my linear pure or impure one-way or rewindable migrations. Wow, that sounds pretty incredible. And then there's a squirrel, scrap your nails. Heterogeneous lists. I haven't used this enough. Release notes. Let's search for migrations. Session migration. Previously, square migration could either be pure involving only the definition or impure. Okay, let's take a look at this. Allowing arbitrary IO, but they had to be rewindable. That is, every migration step had to have an inverse. Square 06 generally is to allow both invertible and one-way migrations. Coordinated type for migration, the free category path has been moved to its own package free categories. Ooh. I like that. Thanks to Raveline, Squirrel 5 introduces the function default main to easily create a command line program to run or rewind your migrations. Very cool. Previously, Squirrel's migration were impure, allowing in addition to running definitions to run arbitrary IO operations, such as inserting data into the database or printing out status messages. In order to provide compatibility with other migration systems, Squirrel 5 introduces pure migrations. That is, migrations that are only definitions. Migration P, schema 0, schema 1, migration name, text, up and down. So those are, I think, yeah, clearly there are invertible migrations. A pure migration is migration definition. So definition being this path, I suppose. So let's see what I presume things are going to be here. And migrations are going to be in other definitions, and I think they were in sessions, right? No. Let's look again at this. Yeah, session. Migration type to safely change the schema of your database over time. So not some extension, define our table type. Emails table. Around the kind of define migration to make our table. Parameterize giving the option of a pure one-way migration definition, impure one-way definition, index PQIO, pure reversible migration ISOQ definition, impure reversible migration ISOQ. And so migration definition, I suppose, is the simplest one. And he defines here the ISOQ definition. And ISOQ, I suppose, the one that's going to basically give you the up and the down using this ISOQ type. And indeed, migration ISOQ gives up and down. Let's look at what is ISOQ. ISOQ, ISOQ. Who are you? You are not here. You are re-exported, so therefore, or you are, yeah, you're exported, so maybe you are, maybe you exist somewhere else. an instance of ISOQ migratory. Yeah, so you must be defined elsewhere. Where would that be? I suppose I have to search for it. ISOQ. Apparently not in this library. So could it be in the free category? Possible. And indeed it is. It's the quiver and arrows of ISOQ bidirectional edges. Show me ISOQ has up down. Excellent. That's what we want. And so he defines this migration with up having create table and down having drop table. And then he can use the category instance to chain migrations together. So hold on. Because you have make users and make emails, and they're both ISOQ of definition and being chained into a path. So then that sort of means that the vertices in this category, or the objects in this category, are schemas. And so make users before that arrow is, or that category or that migration is ran, doesn't have users, and then yeah, and I suppose emails depend on users. Is that the thing? Table users table. They do. This type level thing allow you to say what the that's indexed. That's why ISOQ is actually indexed as well, isn't it? ISOQ has C. Okay, this is a bit hard to read, but here migration ISOQ definition sounds fine, but it also, for some reason, has these type annotations there. Type level lists, which are, seems like more like type level maps with a key. And then this one says, basically defines that migrations depend on things and are indexing these lists of things that are added by each migration. I like that a lot. And using free categories for that sounds quite interesting, and I'm not sure how that works, but that sounds very interesting. Especially because it seems like we define all of our categories here, and that's a quiver functor. It's just a functor arrow. It's not a functor instance, it's a Q functor instance because of quiver functors and quiver monads. Interesting. I was contributing to that. Some smart people using indexed applicatives. Q traversable. Type align sequences. Joachim, that's probably Joachim's Breitner. some disagreement. But trio realize point 2 is wrong. Index applicatives is a fascinating concept that I'd like to have a careful think about. An index monad from the perspective of category theory is a category enriched in the monoidal category of vendor functor unasked with monoidal product given by functor composition. So enrich in the monoidal category of vendor functors unasked. A monad is the monoid object in the monoid category of vendor functor given by functor composition. Applicative is a monoid object. Yeah, I'll get back to this. At some points, I can iteratively deepen into this. I have been there, but I need to relearn a little bit of jargon here in order to understand that. But indexed comonads in particular are going to, I want to talk about this just a tiny bit because that relates to the co-effect thing, which I've been keeping on the side, but that was one of the most inspiring things. Co-effects is therefore one of the other reasons we want things. And maybe linear types. Seems that maybe they could emerge from that. Okay. Okay, so this is too hard. And Comonadic composition. Right, so then what is there such a thing as a ZP composition? Which is maybe, which is not the Cartesian product, it's just the pointwise product. And yeah, when I was looking at deconvolution of comonads, there's the possibility that yeah, you can do comonad optics, but that's store T SWA is isomorphic to day store S. So yeah, it's basically saying that comonad transformers can simply be derived from deconvolution. So it's kind of maybe the reverse. The deconvolution is the more general pattern. I'm not so sure, but is using this to say that we can write optics to focus on the store inside of store T. Yeah, that's super funky and pretty amazing, because this actually also makes me think about Ed's talk on monad transformers and focusing. He was talking about some kind of lens to go inside that stack. Lift actions to corresponding monads. Whenever we have a comonad optic which identify one monad as a deconvolution of a small comonad, can be useful when using comonad to describe user interfaces. I think with Smash, there was there optics there? There might be a lens which focuses on the specified label in a Smash product. There is, and it might be a generalization. If I suppose Smash itself uses the convolution, which clearly it does. So I think, okay, so Smash has both lenses to go into specific comonads and uses they to transform to make them comonad transformers. Cons. So day is only shown here. Representation is abstract but can be understood in terms of definition of day. An fx, a jy, and an x to y to a. So for Smash product of several functors, we need a supply of x. We need a supply xj of existential variables. And then we define blah, 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 and then the product of xj to a, which is kind of an uncurried version of x to y here. So he must be then using pure scriptisms in order to be able to do this, which uses the row polymorphism, not row polymorphism, just row types, and then the way to do row transform rows into lists with type level machinery. And then if I am to see day somewhere here, but well, day is going to be in each of the individual comonads. It's not. So it means that somehow Smash is once and for all creating all of the composition. So we don't run the n instance with the n instance problem here, because we apparently are able to simply generate automatically the day instances, I think. Constructing, holy moly, there's a co-smash. Is that part of the example? Because there is an example. It is not. So that's interesting. I'd like to see how that works. Constructing action in a comonad. Oh, holy moly. This means, I think this would take a stack or a row, a row or type level list of effects, of co-effects, and allow us to pick allow us to construct monadic actions in any of those comonads using this. L L is a proxy L. is so L will be just the a symbol, so a type level singleton of a symbol, and then F would be, well, some kind of interpreter, which is like kind of the continuation. So that's going to be very similar to the Co or Co-T transformers. But then here, yeah, we need the Co-T in order to be able, I think, to go all the way and introduce monadic effects somewhere in the stack. Effects in the Comonad stack is the other big question here. And so here I'm suggesting that maybe a Co-T smash is a potential avenue to explore. So another one is the question of how and where we put our interpreter, right? So I think I've asked this question here. In principle, do effect co-effect really need to be interpreted running in IO effect? In practice, we want to run in effect unit or IO unit, and we use monads to describe effects in PureScript and Haskell. But right, so this question, could we have a programming language which interprets Comonadic co-effect directly? And is it what the ThomaSP co-effect is about? Is pretty much the case, but I haven't looked at the implementation yet because it's in F#, unfortunately. But we are going to try and do a little bit of that, and I want to talk about the co-effect interactive paper here. And that will get us to what I wanted to cover here today. So there is another question that I think is also important. It's comonads for multi-cursors or ranges. And I've asked this question before, and there was this mother of all comonad post as well. Super interesting. Let's say that store is the mother of all comonads. But also there was somewhere in one of these posts, I think the person, Brad, says, don't use comonads for this problem. Comonads are great when you need to update one value based on its context, but are awful at updating multiple values simultaneously. And that I think is something we definitely want to check. Because if that's the case, then I need to rethink a few things about comonads for databases or queries, which, as you see, I haven't added here. But this might just be a question of what we mean and how we do things. Because one of my original ideas was, oh yeah, we could have, instead of having a type of a position, like in the store comonad, we have the type of cursor. What is it? Pursuit and store. S is the type of the index, and A would be the type of the value that's contained in the store. And so my intuition was, well, you just need to say, well, store range A, where type range is something like maybe a set, or even just a list, right? Maybe an array of S's. And ultimately, maybe we say, actually, we want to store query of A, or maybe even a store length of A. And that's weird because store already look a bit like lenses. And that's something we've looked at before. And I'm going to try and find like coalgebras for the store comonad. So, dude, that's just what, that's just crazy. Store comonad. The other thing that's crazy is that in the in here, oh no, it's in the mother of all comonads. So that's in here. They basically say that there's a more principled store comonad that's lurking inside the actual adjunction of between the continuation monad and the store comonad. So apparently it's a different formulation. Where is that written? Mother comonad, store is equivalent to comonad. And that's weird, and that's pretty interesting. Apparently it's related to density and codensity in some ways. Content store are definitely opposite of each other. Hold on, there was a place where someone said that the store derived from this adjunction is not exactly the store. Ah, yeah, there we go. It has a property that context T. Okay, so that's another transformer right there. Context T is a comonad transformer that is to density what cont T is to codensity, apparently. And I don't know what that means. But it has a property that context O identity is isomorphic to store O, but is different from the store T seen in various libraries. And well, that is so puzzling. What is this store T? So many questions. Okay, right. So this whole with a range. Yeah, I kind of start to get it as it's said here about using the comonads to update multiple values. Is because, okay, let's say you extract a range and that includes several values inside your store. I mean, maybe it's okay as long as indeed, like you have queries and mutations that are defined in terms of ranges. But yeah, I suppose the question is updating multiple values in the extend way would be somehow moving this range across all your space. And maybe that's the part that is not obvious. But in truth, expand with databases, extend, I mean, with databases is going to be a little bit, it's going to require some sleight of hand, I think, because we don't, well, first of all, it's going to need to be lazy. And maybe that's enough. Maybe if it's lazy, then only when we actually query the value, then do we do we do IO, right? Like query the database. But then there is still a question of how do we formulate sweeping or scanning or exploring all the potential spaces when you have something like a range. Do we have to do all of the permutations of any finite length range onto the database space? That's a big question. I'll be right. Okay, so food has arrived, so let's just close this. So maybe by asking, indeed, how do we think about moving through all possible ranges of a state space? Okay. And then going back to effects in the Comonad stack, so we have this Coty smash direction. We have the question of do we put with Coty, it seems that we can put IO in Comonadic values. Can we not instead do this in the interpreter? And so that, to be honest, starts to feel like Explore M. And isn't Explore M sufficient? And it could very well be that it is. So that's really something we want to try. How could I make it so that I remember that we want to try that? By doing something like Explore M would be, we need to, interesting. We just need the Explore M to include interpreters, I think. with the components. Do we want the component to wrap their interpreters? When we put Qt inside, we kind of mean that. And I mean, I like the granularity of being able to swap interpreters at the component level, as opposed to when you run your whole program. But maybe components can still be aggregated outside of, meaning if you hang those components inside a React component tree, then you can still explore each individual bits. Might not be the most elegant. But what am I trying to say? Here, I think that's what I was doing. Maybe I was passing some kind of effectful thing, right? Input was trying to wrap, and that looks quite a bit like an interpreter, doesn't it? It takes the monadic action, returns an effect unit, and then maybe that returns in turn an effect unit. So that's interesting that we got to this shape, because that sounds like that's really like F. That's kind of a little bit like this guy, maybe, but not really. But maybe it'll make simpler. It will make this things. It will make things simpler if we try to define this in terms of explore M. I want to just check something as well, which is that how about here? Is there an explore M? There isn't, right? There isn't. And hold on, the shape. Yeah, the shape is really, unfortunately, nothing like explore. And that's interesting in itself. Maybe going back to a similar shape than explore would actually be fruitful. And so maybe I'll just say this here, and maybe like so. Yeah. And we want the co version of that. We want sort of flip, because we want to have co-free, and then we can kind of return in any monad. I think that kind of makes sense, right? We might want to make this like kind of like pairing instead. Which we actually maybe won't even need to specify, because if it's free and co-free, then we have a pairing. So we won't need to say it. And in fact, that I think is sort of what happens with run Qt. No, run Qt doesn't need the pairing. Yeah, it's weird. Like the pairing is done sort of inside. And I think maybe we can pull it out. The fact that we build this co-free here with the interpreter, I think we can avoid that. So this should allow us to avoid building co-free with the interpreter. Yeah, I think it will delay the use of the interpretation, I think, correctly. Meaning we won't have to thread it through, meaning that we won't have to make our comonads co-effects, at least in the Qt sense. So I'll need to rethink that. So as promised, I'll just spend a little bit of time explaining co-effects first of all, there is a little bit of a conversation in the PureScript Smash. I think it's in Smash. In the issue, it's like, is this really co-effects? And seems like it maybe has a different terminology. So that's useful because here he sees maybe call them Comonad-derived monadic effects or something. It's not really the right thing since the monadic bit is somewhat separate. So that's sort of unclear. So let me go here and do a little co-effect section. Are Phil's co-effects the same as Thomas's? And so that's unclear. And so that's an important caveat before jumping into Thomas's, and that's without an H. So what's this about? Well, the idea is to say, well, actually comonads and or context, which is really what co-effects are about, and comonads are about, is in fact something really key. And he demonstrates how that's the case. So stencil computation are an example of comonads being used in, for instance, like the Conway game of life is actually a stencil computation, and that's fairly well known. But he explains that co-effects basically define the context of a computation, and a really interesting aspect here which really hits a really important difference of effects and co-effects is that if you define a clock in an effect way, then you'll only be able to make it so that the clock gives time at the moment where you call the effect. Meaning you kind of wrap the code that says get time into a function, into a thunk, into a recipe. And then the moment where you actually run it, which in a compiler, when you're actually talking to hardware to get the clock, will happen in the runtime. At that moment, then the function will be executed. But with a co-effect, you can actually decide when that's going to happen. You can decide that actually at the co-effect creation, time will be logged, or at the co-effect execution. So either at the on the server side, for instance, or the client side. And that's pretty interesting because it means that actually co-effects have maybe more expressivity. So that's an important bit. Okay, co-effect, maybe more expressivity with regard to how is it? Is there a way to call this? Come from the right. In effect system, the effect of the function body are always delayed. Printing inside function body will happen when the function is executed. Co-effects are different. Say we have a function that requires a clock. We construct it on the server and then send it to the client. The clock can come from the declaration side or from the call side. With regard to declaration, call site, effect execution. So that's pretty interesting already. We see that maybe there's more expressivity there. Something else that goes on is that you can apparently also decide to annotate individual variables. And this live dead example, that feels totally like if you track variable use using a little bit more than live or dead, then you have, it seems like linear type. It seems like being able to carry around a vector of whether your data dependencies are used or not used, have been used once or don't exist in the body. All of this allow for optimizations to occur that might not be available otherwise. That's why I wrote linear type here. And so compiler can eliminate date variables as well. And then comonadic semantics means that maybe we can use comonadic composition in order to add things to our language. And the fact that we can do this in an extensible way, as pointed by with Smash, for instance, with PureScript, I think that's going to give us superpowers. Except that, yeah, when I read this, I was like, oh my God, I want to implement a context-aware programming language. But we've been resisting a bit the writing a programming language thing because writing an operating system is already crazy. So writing a programming language is even more crazy. But I'm going to write it here. Programming language, because I suppose that's what a Hascaller needs to do at some point. I mean, I think I have it in I have the idea of having a programming language because I have stay connected to lambdas and compilers and PL right here. And what I mean here really is sort of write my own programming language. So it would need to be a context aware exactly in this way. And I think using PureScript might actually bring surprising results. I don't know if there are many compilers in PureScript, and obviously the fact that it would run in JavaScript is a bit weird, but what if you have a compiler in your browser, right? Anyway, well, let's not talk about that, but other potential uses here, what Thomas called two core effect languages. One would be tracking parameter use. So implicit parameters would allow to do something like being able to know whether what a snippet needs in order to be executed. And by the way, I learned that apparently Haskell, in the actual paper, Thomas explained that actually Haskell has an implicit parameter extension that I didn't know, which kind of does that. Parameter extension in Haskell. Implicit parameters. Let's look at the wiki maybe. You can use the comma, the exclamation point thingy, and that will make it so that parameters are tracked as a constraint somehow. And that means that it will only compile if at the call site you define the parameter. So it's a way to track parameters. And interestingly enough, this can lead to ways to decide whether parameters, or use the type system to track how parameters are needed or not, and even use this data to actually, for instance, like here, generate a UI component to say, well, actually, I know I need these components, I know I need these variables, and so you're going to need to give it if I want to be able to compute. So it means that basically not providing those parameters will be a runtime error. So that's kind of an interesting level of correctness, especially if you say, well, not providing it is a runtime error, therefore I generically derive or create input fields initialized with the default, and then therefore, like here, I satisfy my code is always runnable because I'm able to provide same defaults and yet provide the user with the ability to modify those parameters. This, I think, is next level. Also, it means that you can reason about parameters that are nested within each other. And that happens, I believe, through this index monad capability. In fact, when you look later at the theory side of things for the implicit parameters, it, I think, shows that how does it work? Yes, that implicit parameters require a tuple together with the lookup function that returns the value of an implicit parameter with the given name. So you're wrapping n tuple to combine two comonads that interpret the implicit parameter language feature. You provide a tuple that will track all values that are needed and consume them as they are provided. So that's pretty awesome. And then, of course, we have data flow ability, and that's an actual implementation of the essence of data flow programming paper. I don't know how faithful it is, because right now it seems like it's mostly providing previous semantics, meaning the ability to look at previous value in the stream. Whereas the LVS comonad in the essence of data flow programming also provides semantics for future values, which I'm really interested in because I think it will allow to create small programs that actually will run in the future, or say that they depend on the value that is going to only be available in the future. Something that's really amazing is that coeffect tracking how many past values are needed indeed mean that you kind of solve the FRP problem of how much history do you need to keep in a statically typed way. And that's, I should write that down somewhere, because I think that's, I haven't heard that elsewhere. So when we say, you know what, this should be a whole section. Right. The fact that allows to know statically how many past variables you'll need seems to solve the time space leak problem in FRP, maybe even a more generalized one that Ivan Perez mentioned in the time traveling talk. Because in the time traveling talk, Ivan Perez kind of says, oh, we've been removing that buffer, the ability to, to try to make FRP efficient, we don't keep values across all time, but actually we might want to reintroduce that if we want to, for instance, allow to reverse time and manipulate time in games, doing time traveling in the back and forth. And it seems like with a data flow language like that, you'll be able to statically define how much buffer you need to keep, and that is unheard of, and seems really compelling. So static and dynamic scoping, and write some examples here. That's the example of the data for programming. So if we say prev of n and check the snippet, it would say that it needs n2 as well in order to know how to calculate. And right, then there's an approach where if we say things can be analyzed either by having a big data type that tracks for the whole body how many pass values are needed, or they track this at the individual variable level, and that's called structural coeffects, where instead of keeping a you're able to annotate whether each parameter is needed with a time buffer or not. So here x is not needed, doesn't need a time buffer, whereas y needs a buffer of 1. And in the actual implementation, this is showed to just require to carry around a vector of pass value needed. Maximum number of pass values will be if you carry only one annotation for all variables, and here you carry a vector of annotation for each variable. And then, so therefore, x plus prev y will attach 0, 1 to xy, which means that you need only the 0th. You only need the current value of x, and you need one value back in time of y. And I think those things, if you then start to say, well, how about -1 for values in the future, they would still work. You'd be able to do smart scheduling with that, where you'd be able to say, well, I'm only going to need this value in 10 clock cycles. Therefore, I just schedule now something that will be woken up in 10 clock cycles rather than having to check on it every clock cycle. And that's a very efficient way to deal with that. So again, I think an idea that is not explored. So maybe here, maybe future values a la LVS, tracking with structural coeffects will also allow to optimize the future scheduling loads, which sound a lot like it sounds like a variation on clock type composition in Rhine. Because if you know if you have a master clock, you're still able to, you can define maybe who is the master clock and distribute the load on the scheduling, or which is the clock that is good enough to be able to do your scheduling in a way that all of your schedules are going to be able to run properly on time. You can probably do batching and things like that. That's batching in time, where you schedule something just a little bit before you're going to need the more granular scheduling, or something like that. You wake up a more fine-grained scheduler a little bit in the future that should allow to, not have too many things that are checking time all the time. So it's kind of like an optimization of the event loop, basically. Okay, and yeah. By knowing how many pass value we need, we can pre-allocate a fixed size buffer to keep the pass x and y coordinates. So that means that runtimes for this kind of languages can be really smart, and I like that a lot. And then, but it also, like here, we see that there's something so different from from what I've seen before, is that I don't know why, but like all of these things about annotating the AST basically, and then how that maps onto these comonads, like in fact these index comonads, I think in this case, it's yeah, it's so this is F sharp, unfortunately for us. So I think we'll want to rewrite the coeffect paper in pure script. That's going to be pretty cool, I think, because yeah, these are, I think, type level tuples. No, yeah, those attach a label. Yeah, it's a lookup function for this. Right, so that's actually the store comonad right there. So this is actually a composition of your base comonad for, so it's actually a comonad transformer for any, what is primate there? Oh, yeah, I think that's the base comonad, right? I think so. But we'll need to look a little bit at the code, and then I'll also want to know, so before rewriting things, look at the code and find out about how monadic execution is dealt with in this comonadic context. Because I can see that in the basically in the compiler, or maybe interpreter, like here an interpreter clearly, the code is parsed, and then that gives rise to building up an AST, which is maybe expressed in terms of a comonad itself. It might be. There's this thing like a ABT. Is that a comonad? An abstract binding tree, right? That exists, right? Yes. And is that a comonad? There is a tree comonad. Structural notion of context, but so oh, that old thing. Coeffect playground. So that's the F# code for the coeffect playground. So really what we mean is actually this here. And right, there's some JavaScript, and then there's some F# outside. Mostly here there's a parser and translator and an evaluator. Let's look at the translator. Coeffect translation that translates source language. Let's look at the parser. AST. So coeffect AST is here, and the AST is a good old multi-type token coeffect thingy. A good old expert type. That's an expression in the coeffect language. And maybe in the paper it's actually better. The paper PDF. And the parser, or the ST. Structural index. Emerging context. So it doesn't go into some of the implementation of the, it's more general, because I suppose there's not necessarily a contribution here in terms of parsing and whatnot, but there's something like the expr type expression. I mean, the typing rules, I suppose those should be completely equivalent to defining, I think, those the expression types and so on. Application variable, I think those basically define things. Merge split, so those are Comonad, that's the specific coeffect Comonad here. Coeffect Comonad has merge and split. That's explained somewhere. Now I'm a bit lost with these things. It's explained. Yes. Merge and split. Here, merging and splitting. For coeffect, we need more than plain comonads. A plain comonad gives us a way to represent sequential composition. So that's interesting, right? So you kind of saying coeffect, talk about comonadic sequential composition. To capture the semantic of the programming language with context, we need more. Programming language, we need to combine merge context and split it. So that sounds like you want a category with products and co-products or something like that in your comonad. I'm not sure how that works, but so you do have a coeffect algebra. Right, so some of these are about sequential composition, and others are about right. This is split here, and yeah, and this might be merge actually. Oh, no, all the effects are delayed. No, so that's something else. But that might be actually sequential. That might relate to sequential composition. Oh, marriage of effects and monads. What is that? So that's about the when things are executed. Maybe I'm not going to read that. in the papers on coeffects. Yeah. And he calls translation coeffects in a single type system and a single translation mechanism works for multiple different systems. So let's take a look at what translation does. Coeffect translation and translate. FontScript TypeScript, translating F# code to JavaScript using FontScript. So translate actually does the translation. So let's take a look there. It takes translate, which compiles, compiler coming from FontScript compiler, and it compiles Q, which in our case is coeffect GUI main. And I think where is that going to come from is unclear, but yeah, some stuff is replaced. There's an expression replacer that creates unsafe versions of things, apparently. Use system string. Okay, that's just a replacer that takes char and returns a string, apparently. Yeah, and then the script is going to be outputted to script.js, and it's going to be full of that coeffect.gui thing. And the coeffect.gui thing is probably here, and it does jQuery things. It uses FontScript to do things, but it calls AST pretty and evaluation, so it's probably at the end going to do sets up tooltips, has a main, which depending on modes is going to do different things, and maybe evaluate. Yeah, let evaluate XS. Set live chart function is going to that's for a live chart, and this so evaluate x's y's. We're going to make args be x's of array in, so somehow piped into an array and mapped as a number in the list Comonad, apparently. Because I suppose maybe that's a bit tough to understand. Evaluate here takes a unit, and we want it to kind of give us source code somewhere on keyup. Evaluates, which traces event that it eval past values, and also uses this Comonad. So having some args having passed. It's possible that don't understand how code is being passed here. Maybe inputs, generate list inputs and output tables. Unclear. I don't really know how to read this. Coeffect kind pass values, implicit params. Okay, pass values I think is the data flow programming examples, and implicit param is the implicit param examples. And there's an input that says implicit Comonad here compared to input which matches type funcs there, but could it be that it's the list Comonad there in that case? Not sure. As input value tuple with the list Comonad in there. So maybe implicit Comonad is then passed somehow to some evaluation function in a place that I can't quite see. Input table result must be something that passes. Okay, can't really see it in GUI. I think it's going to obviously take me more time to understand this, and it could be that this question, the core effect one, the merging, no, not that one. The effect in the Comonad stack. Right. So here there's look at core effect playground. To find out more about practical use of Comonad-based language, including how are monadic effects interleaved. But I would say that it feels like maybe explore M really is the way that we want to deal with effects in the Comonad stack. But interesting to see whether somewhere it exists in there, and it could be that it's better to look at it in the paper, although yeah, it sounds like the paper is really not about implementation somewhere. It's really about like the all of the Comonadic building blocks to build these languages. Or maybe there is a question to ask, is like how would maybe ask Thomas Petruchek, how would such a co-effect language run monadic actions like printing and querying the database, right? Okay, I'm going to stop here. That's already quite a lot. And yeah, thanks a lot for watching. That was Comonadic Exploration 8. In Comonadic Exploration 9, we have way too many things that we could ever dream of actually finalizing, even in Comonadic Exploration 90. I would say there's enough work for the for Comonadic Exploration 90 here. So we have to pick one. And I think it's probably going to be about effects in the Comonad stack, and probably about using Explore M. And so going back to our code in our Comonadic playground and try and find a way to make this interpreter not be threaded through, and maybe that will give us a little bit of space to move forward in actually having actual code run into these things, and then maybe we can go back to having more of our theoretical explorations and exciting things about writing a language around all of this. And all right, thanks a lot, and see you on Tuesday evening for more Comonadic Explorations. Bye-bye.